Hello, my name is Jack Montoya, and this is Physics 2211, Lab 4, Oscillation of a Spring. Here is the order in which I will discuss the experiment and the discussion of this lab. This week's lab is a two-part lab consisting of a tracker model of the motion of a spring as well as a computational model that matches that motion. Then we'll be looking at energy graphs that have both the changes in potential energy and the changes in kinetic energy, with the total energy also displayed on the graph, the sum of the kinetic and potential. And then we will compare the x and y positions of both the experimental and the computational model. Since this lab is all about energy, we need to understand the important physics concepts that have to deal with energy. This includes the momentum principle and position update formula, since we are dealing with motion, as well as the energy principle relating to kinetic energy, potential energy, and work, and some specific examples of potential energies, such as gravitational and spring, as well as the force on a spring. Here are the initial conditions for the computational model. We can find the initial position of the mass using the coordinates on the tracker, and the spring constant of the spring being used can be found using the force equation for a spring. Lastly, L naught, the relaxed length of the spring, can be calculated by holding a mass at static equilibrium with the spring we are using. For the computational model loop, from the top down, I used multiple equations from physics, including the gravitational force, the spring force, the velocity update formula, the position update formula, and a bunch of the energy change formulas, including kinetic energy, gravitational potential, and spring potential, in order to calculate energy changes and update the position of the spring, similar to other labs where we observed motion. In the resulting change in energy versus time graph, we can see that delta U grav, the change in gravitational potential, and delta U spring, the change in gravitational spring, are mostly equal and opposite throughout, while the delta K, the change in kinetic energy, is much less in magnitude. And we can see that the delta E, the change in energy, stays constant at 0 because nothing outside of the system is doing work on our system. Looking at the resulting position versus time graphs, we see that my y positions for the model and the experiment were nearly identical, while the x position for the model and the experiment had a much greater difference. As I said before, from the energy versus position graph, we see that energy stays at a constant 0 because no work is being done on the system. However, in reality, friction and air resistance will be doing a dissipative work on the system. Some sources of human error in this experiment could be human error in the tracking, possibly messing up the center of mass, and error recording the video. Is the energy principle satisfied from my model? Yes, I believe it is satisfied because no work is done by the surroundings, so the change in energy on the graph should be 0, which it is. As for the oscillation periods in the x and y graphs, I calculated them to be 1.6 seconds in the x and 1.5 seconds in the y. This is most likely due to more friction when the object is moving in the x direction.